So I didn't receive any emails or any questions in advance. So if you got them, I got the chat open. Otherwise, I'm going to do a little bit of reading here off to the side, but I got the chat window open in case you got any questions. You open test 3, homework for go 1, need help with 4 part for 58.59. All right, let me open up that assignment. So design a synthesis of cis-2-methylcyclopentyl acetate from trans-2-methylcyclopentanol. So you're definitely looking at an inversion of synergy. So you got this right idea with the tosylate. Give me just a minute to bring up any programs I might need to use. And I'll bring up the desktop. So good for you. So you got the right idea. So they want you to actually start with this thing on the right, which I find incredibly obnoxious to do this. So you start with the thing on the right, you make the thing on the left. So inversion of symmetry is the easiest thing to do here. So if you start with the O-tosylate, that's the easiest thing to do because you can easily make the tosylate complex by reacting it with the alcohol. So if we look at how, let's see here, what's the next part? So now if we look at it, it asks what reagents to work with. So the first reagent here is going to be the tosyl chloride with pyridine. And then to react away the tosyl chloride to give us this ester, we're going to work with the ester. In this case, it's, where are you? There you are. It's going to be the base form of, basically, this is the acetate ion. So you had the right idea is that you would want to start with the alcohol, hit it with the tosyl chloride. The tosyl chloride will give you the tosylate complex, and then invert that with the acetate ion. Question 59. Design a synthesis of cis-4-tert-butyl cyclohexylcyanide from trans-4-tert-butyl cyclohexanol. So you want to make this complex from this complex. This is another one. The big thing here is the switch in symmetry. So we have the OH group here as wedged, and we want to switch to the dash conformation. I'm sorry, we got a dash, and we want to switch it to a wedge. So the easiest thing to do is have the tosyl chloride complex here. So if we start with an alcohol, we can easily convert the alcohol to the tosylate complex, and then use something like potassium cyanide to flip it over and give us that complex. So if I do that, that works. And then if I start with the alcohol, that's what you're going to work with. So you can start with the alcohol, react it with the tosyl chloride to give you this complex, and then hit it with potassium cyanide. So the next part, yes, I know. Yes, move on. It asks you what the reagents are. To go from the alcohol to the tosyl complex, just tosyl chloride and pyridine, and then potassium cyanide in some type of polar aprotic ether. And there's your synthesis. Question, confused why it would not be any of the other tosylate combinations. So let me go backwards one question. So if you're asking why it wouldn't work with any of these, in terms of the alkene, they're probably, you can try, for B, you could make this work using peroxide and sodium borohydride. Or I'm sorry, not sodium borohydride. Why am I drawing a blank on what it's called? B2H6. That complex. If you use B2H6, it'll give you the alcohol, but it's going to give you a mixture. So B here could be converted that, but you're going to end up with a racemic mixture because the B2H6 with diglyn, that's pretty much like, it's not stereospecific. You really wouldn't want to work with the alcohol here just because there's no way to go directly from this alcohol to this alcohol. On top of it, I mean, in principle, you could make this work. There are definitely condensation reactions that you can do with alcohols here. So if you were to basically distill this complex with acetic anhydride, which you haven't learned about yet, this reaction would work. It would totally work, but the problem is, how do you convert this alcohol, which has the wedge, to this alcohol, which is dash? There's no straightforward way to do it. The halogen here, in principle, you could get this to work. The problem here, I think, is more just the tosylate complex is more selective. So yeah, if you took something like this and worked with acetic acid or sodium acetate in a aprotic polar ether, you might be able to get this work. I think this is another one that kind of suffers from you're probably more likely to get a racemic mixture than anything else. And then obviously, if you could go directly from here to here, E is just kind of the filler answer. There's no direct way to go from here to here. So this E answer here is kind of a nonsense answer. And then as far as where you start out with this, yes, B2H6 is diborane. Sorry, I was just trying to blank on what you call that. But B2H6 in diglyme, and then it's a couple other steps like sodium hydroxide and peroxide. That's the way you add alcohols to alkenes in a anti-Markovnikov fashion. So if you had this complex, and if you heat this in the presence of water, let me draw it out the products. So if you heat this compound here in the presence of acid and water, you will get an alcohol, but the alcohol you're going to get here is this one. You're going to get the 1-methyl cyclopentanol. If you do the B2H6 diborane, you'll get the alcohol, but and it's meant to be an anti-Markovnikov addition, so it goes to the least substitute carbon, but you're going to get both the wedge and the dash forms. Wow, this would make a lot more sense if I actually showed you the desktop. So if you take this complex here on top and just heat it with acid and water, you get the alcohol on the tertiary carbon. If you do the B2H6 and heat it, you'll get the alcohol on the secondary carbon, but you're going to get both the wedge and the dashed. So again, I can kind of see how you could start with this complex and make it work, but there's really nothing to be gained by working with this complex. It's a lot more steps. To get back to this one, how do you make the tosylate complex? This is super easy. You definitely want to start with the alcohol. The tosylate is only going to work with alcohol. So this one, C won't react with the tosylate, B won't react with the tosylate. D already has a tosylate in place. You'd have to invert it, and there's no straightforward way to make that happen. And then E is the same thing as B. It's not going to react with a tosylate ion. And then as far as the rest of these go, TSCl, the reason we want to work with the TSCl, that chlorine there, I can draw the structure of it really quick, possibly. So this is the tosyl complex, and specifically this is tosyl chloride. This Cl here with the oxygen, this is an incredibly weak bond. So if we work with, ultimately what this wants to become is this complex here. When you go to take on organic 2, we'll talk about carboxylic acid derivatives. It's going to follow the same pattern of reactivity, which I know doesn't mean anything to you right now, but TCl, this is going to be the most reactive complex because chlorine's easy to break. The OH, TSOH, this is completely unreactive. This isn't going to do anything because this is the most stable form. So if you take TSOH and react it with your alcohol, it's not going to do anything. This weird ester they're showing here, So this TSOOCCH3, it's this complex. This is an ester. It will react, it's just not very good at it. TSOCH3, this is an ether. Ethers also aren't very reactive towards this reaction. So these are all tosyl complexes, but the thing is the TSCl is the most reactive. And the SOCl2, the thionyl chloride, what that does, I can bring it up. So if you start with this complex, so that's what they've got drawn here. I'm just leaving out the hydrogens. And you hit it with SOCl2, what you're going to create is this cis 2-chloro-methylcyclohexanol, or 1-cis 2-methyl-cyclohexanol, or cyclohexane, cyclopentane. Ugh. So this SOCl2 here doesn't have the tosyl complex in it. It'll just get you inversion of symmetry. But yeah, the big point here, the reason why these other tosyl complexes won't work, 1B is completely unreactive. C and E will react, but your tosyl chloride is definitely your most reactive. And then these, this is an aldehyde, doesn't undergo any type of substitution reaction. This is what's considered an, what's it called? An acyl halide, acyl chloride, not likely to react with the tosyl complex. Your acid here may work, but the whole reason they're throwing into the H2SO4 is to make sure that it's not in the acetate form, so it's not likely to react. And this ester here, CH3C, where are you? I can draw it out for you. This CH3COOCH3, it's this complex here. Also, it can react, it's just not very good at reacting, and even then, we're not trying to go for it. So we like this because it is the acetate ion, it's CH3COO negative. That negative is going to work as a nucleophile and displace that oxygen off. So some of these are like syntheses that could potentially work. I just think they're looking for the most likely to work. So if you're curious, well, like some of these, well, why wouldn't they work? They may. They just may have really bad yields and really bad issues with stereoselectivity. Yeah, you're welcome. So, questions asked. I've watched the videos, read through the PowerPoint. I've begun the test your study packet for Article 1. At that point, you should be well prepared. Big thing with a lot of these syntheses questions that you'll see on like exams, it should be any more than 2 to 3 steps. The third test is the culmination of the hard part of the material for Organic 1 and even for Organic 2, because you are seeing this. Like, there's a lot of reactions to keep track of. The nice thing is that when we go into test 4, you've kind of got the stereochemistry down, you've got a feel for how reactions work, and you've got a feel for how the naming works. So if you can get through test 3 and you're feeling at least kind of on top of it, test 4 is easy, and test 5, the final exam, while it's cumulative, is still pretty straightforward. So this represents the culmination of the hardness, getting reactions down, remembering the stereochemistry. And yeah, if you can go through those packets, you know the reactions, you know how to name, you know how to draw the stereochemistry, you're pretty solid for the exams. You're welcome. All right, Orgo 2, question 60. Let me load it up. All right, complete the reaction and show how butanoic acid can be prepared from 1-propanol. So we're starting with 1-propanol. Where are you? It's 1, 2, 3. And we want to go to butanoic acid. So the thing to catch here is that we've got propanol, which is 3 carbons, going to butanoic acid, which is 4. So overall, it looks like we're going to do this in 3 steps, which means that we also have a carbon addition reaction as well. So let's take a look here. So we got CO2 and acid. Won't do us much. Oh, that's clever. I like that. Okay, so first thing we need to do is do a carbon coupling reaction. And it looks like they're implying here, so Mg dimethyl ether, this is the recipe for a Grignard. Chromic acid is oxidation, this is reduction, HBr would be a substitution. This would be hydration of a double bond or an alkene. And we're going to get back to this CO2, but this is actually a reaction I talk about. Actually, you did with the Grignard reaction. You try to do by making benzoic acid. So if we look at what's here, this compound doesn't make any sense to B2H6 because we don't have an alkene. This doesn't make any sense in lithium aluminum hydride because we don't have an aldehyde or a ketone or carboxylic acid to reduce. This chromic acid will convert propanol to a carboxylic acid, but it'll be propanoic acid, so this won't work. This CO2, H3O+, won't react with anything, the magnesium won't react with anything. So we're going to go with the HBr here, and the reason we're going to go with the HBr is that this is actually going to give us, this is going to give us 1-bromopropane. So I've taken my propanol and I've converted it to this compound here, the 1-bromopropane. Now I can react it. Now the bromopropane here, we've already used up this reagent. Again, this borane doesn't make any sense because diborane doesn't make any sense because we don't have an alkene. This lithium aluminum hydride doesn't make any sense because we don't have an aldehyde or a ketone or carboxylic acid. This chromic acid definitely doesn't have anything to react with. The CO2, the H3O+, they're not going to have anything to react with, and we've already used the HBr. So I'm going to stick the magnesium in here, and what the magnesium is going to give us is the Grignard reagent. So 1, 2, 3. Now the thing to keep in mind with a Grignard reagent is that it is a carbanion. When you really get down to it, where are you? This is really what we have. And if we have carbon dioxide, what will happen is that our lone pair, this carbanion is going to attack the central carbon, and it's going to break it up to give us this compound here. So it's our benzoic acid, but without any hydrogens on it. So it's a benzoate ion. And from there, we can protonate. So again, we've used the HBr. This doesn't make any sense because we don't have an alkene. This doesn't make any sense because we don't have a carboxylic acid present. We've already used the MgBr, or the magnesium. And chromic acid doesn't make any sense because we don't have anything to oxidize. So if we react it with the CO2, we're going to get nucleophilic attack from the carbon here beside the magnesium onto the CO2, and this will acidify it to give it, this H3O+ here will acidify it and give us our benzoic acid. So that was the line of reasoning here. We kind of had to imply it from everything that's here, but again, most of these reagents don't actually do anything. That's kind of why they're there, is just to kind of keep you from like randomly selecting answers. But we start with the 1 propanol, react it with the HBr to give us the 1 bromopentane, hit it with the Mg to give us this propane carbanion, then we hit it with the CO2, which will give us the butanoic acid but deprotonate, so the butanoate, and then we acidify it to give us the carboxylic acid. So that's question 60. You're welcome. So it doesn't look like there's anyone else out there, so we'll just cut it off. Thank you all for coming. And again, if you ever have questions, feel free to email them or put them up in the text box. And I will see some of you about an hour.